All right, on problem number 7. It says, unknown to a medical researcher, 7 out of 23 patients have heart problem that will result in death if they receive a certain drug. 6 patients are randomly selected to receive the drug. What's the probability that exactly 4 will die? All right, so this is another hypergeometric distribution, and we use the same formula that we've used on the last 2 problems. Sometimes it may help to write down what everything equals before you start plugging everything in. I know I haven't done that on the last 2. So I mean, you could say like, okay, well, we're gonna select 6 of those, right? So that's little n. Little n is 6. Well, how many total patients are there? The total patients, that's going to be big N, capital N. We're looking for the probability exactly 4 patients die. So exactly 4, that's going to be our X. And then there's something else there, right? Well, K, how many possible would die? Well, 7 out of the 23. If you do that first, then, you have your formula written down. That, let's see. Yes, this one right here on number 9. Then you just plug all the stuff in. You plug in your K, your X. You say N minus K, N minus X. So it's not too bad. So we would set this one up. All right, we got K, C, X, so 7C4 times. Now you have big N minus K, that's 16, C, and then we have K minus X, N minus X, that's 6 minus 4, is 2. Then you divide all that by big N, 23, C, little n, 6. So you either work this out by hand, doing the combinations, or plug it in a calculator, write everything down, divide it out, and you should get about 0.041605, so on and so forth. So if we round that to 4 places, if that's what it says, a decimal rounded to 4 places, that's going to be 0.0416. Okay, so this is uniformly distributed. That just means it's the same probability for at every increment, every inch here on this problem, because it says it believes the height of cedar trees is believed to be normally distributed uniformly between 9 and 14 inches. What's the probability that the cedar tree will grow more than 11? So from 9 to 14, how many inches is that? Between 9 and 14, we have 5 inches. So that's going to be our denominator. And then more than 11. More than 11, from 11 to 14, that's 3 inches. So if the total possible is 5, and more than 11 would be 3, and that's just simply going to be 3/5, right? This is the total number of inches it could grow. More than 11, from 11 to 14 is 3. You divide there and you get 0.6. So it's just 0.6. Alright, let's see. The diagram below is the illustration empirical rule. Select the missing label for the diagram from the list of choices. Alright. So we have, alright, so the thing about this is it's symmetric. Everything on this curve is symmetric. So that means that this area and this area are the same. So if that is mu minus 2 times sigma, that's going to be mu plus 2 times sigma. Alright, so mu plus 2 times sigma. Because you can tell it's the same amount of area here as there is here. You know, right here in the middle, that's where the mean is. If you subtract 2 standard deviations, you go to the left. So that would mean if you add 2 standard deviations, you go to the right. Remember, that means population standard deviation, that little symbol, that lowercase sigma. Okay. Alright, so this says x equals 50.1, mu equals 48.2, and sigma equals 2.2. Indicate on the curve where the given x value would be. Well, the x value given is 50.1. So I just need to move this to 50.1. There you go. That's where the x value would be. Find the area under the curve of the standard normal curve to the left of z equals 2.17. Alright. So, to the left of 2.17. I know that it has these buttons down here. Those tables are also here. So, if you look at the standard normal table, I mean, you can pull those up here as well. Okay. The way that the tables work is that the table is always going to be cumulative from left to right. So like you can see for a z of 0, right here, a z of 0, that's right in the middle of the standard normal curve. So if we had our bell-shaped curve like this, well, it's not very symmetric, but you get the idea. Right here in the middle, that's where the mean of the set of data is. That's also where z equals 0, right in the middle. That entire area under the curve adds up to be one unit. Okay, and what this is asking us is find the area under the standard normal curve to the left of z equals 2.17. So let me show you a picture of what we're actually finding. So this is number 14. Somewhere under that curve, you know, if you have a z of 0 right in the middle, then 2 standard deviations, 2.17 standard deviations to the right, that's what a z of 2.17 means. So somewhere over here on the right side, you're going to have a z of 2.17. And that problem wants to know the area to the left. Well, luckily, that's the way that the tables are written. All the tables that we're going to use, the main tables for area under a curve, they give us the area from left to right. So if we look up 2.17, that will tell us the area to the left. So I know you can use these buttons here again, but I'd like for you to get used to using this button to get to the tables. And then standard normal tables, negative infinity to z. This is where we can get all of our stuff. So we need to go to 2.17, right? Alright. So right here, that's 2.17, 0.8950. Now pay attention here, 0.8950. So what that means is, this area to the left, all of this to the left of 2.17 is what? 0.9850. Okay? Now, it did say to the left. If it would have said to the right, unfortunately our table can't give us both. It can only give us one or the other. So if you wanted to know the area to the right, which this problem didn't ask us, but if it did, then we would have to say 1 minus 0.8950. That would give us everything over here, because remember the area under the total curve is 1. Alright, but let's just go ahead and put in this answer, 0.8950, because it said the area to the left. And you could even copy, and then you can just come right here, and you can paste it in. There it is. Now it says find the area under the standard normal curve. This one says to the right, not to the left. Okay, that's very important. Of z equals 0.72. So let me draw a picture and show you what we're actually finding here. Alright. So to the right, so right here in the middle, remember that's where your mean of your set of data is, and that's where z equals 0. So to the right of that at 0.7 whatever, 0.72 I think is what it said. So there is some z value around there that's 0.72. And if we're looking for the area to the right of that, unfortunately the table's not going to give us that value. But what the table will do is give you the area to the left of that. So if we say 1 minus the area of the left, that will give us the right. Because again, the area under the curve adds up to be 1. Alright, so let's go to the table. We're going to go to the standard normal table, negative infinity to z. Alright, and we're going to look for 0.72. Now, that's not the answer, but that's what I'm going to subtract from 1 to give me the answer, because I wanted the area to the right. So 0.7642. So 1 minus 0.7642. If you do that in your calculator, you'll get 0.2358. That's the answer I'm going to put in. .2358. What value of z divides the standard normal distribution so that half the area is on one side and half is on the other? Okay, so that would mean the standard normal distribution, remember it's a bell-shaped curve. So basically what this is asking us is, if we had our bell-shaped curve, what value is right here in the middle that would split this, the left and the right, into 2 equal areas? Well, that's where z equals 0. At z equals 0, that splits it into 2 equal areas. And remember what those areas add up to be. They add up to be 1. So this is 0.5 and this is 0.5. Alright, so I guarantee you, if I look in the table at z equals 0, I would see 0.5 as the answer. Okay. Do you want me to show you? Go to tables. Here, here. Look at 0, 0.5, because it adds it, it divides it into 2 equal regions. To the left of 0 is 0.5, which then means to the right also has to be 0.5. Alright, so the answer is 0. can't round that to 2 decimal places. If you did, I guess it would be 0.00. But hopefully it'll just take 0. Find the value of z such that 0.04 of the area lies to the right of z. All right, this is different because we're finding a value of z. We're not trying to find the area. We're trying to find the z that would have this area to the right of z. Okay, so here's what this problem is asking. Let's say we have the bell-shaped curve. So we want to know what z value would we have around here so that to the right of that area is 0.04. All right. Now our table doesn't tell us any areas to the right of a z value. It will tell us areas to the left. So what that means is all of this stuff right here, if that's 0.04, all of this stuff is 0.96, right? So I'm not going to use a z of 0.96. This is an area of 0.96. So I need to look in my table and find the area closest to 0.96 and then see which z that corresponds to. Go back to tables. Standard normal table. Negative. Alright, so I'm trying to get as close to 0.96 as possible. So I just have to keep looking in this table until I get really close to 0.96. So there's 0.94, 0.95. Alright, I need to go to the next. 0.95, 95, 95. Uh-oh, look at this. I see 0.9608 here, but 0.9599, that's really close to 0.96. That's as close to 0.96 as I can get. So let's see what z value that corresponds to. All right, 1.75. So 1.75 is my answer. So 1.75. That's what I'm going to put in. Alright, now this is probably one of the tougher ones, but it's just kind of a conceptual problem. It says find the value of z. Again, we're looking for a z, we're not looking for an area. Find the value of z such that 0.8064, the area, lies between negative z and z. So the negative z and z will be the same number, it's just that one has a negative in front of it, one doesn't. Let me show you graphically what we're trying to figure out. So we have an area of 0.8064. Alright, so in a way we have to use symmetry here. Alright, so I'm trying to figure out that this one will be a negative z and this one will be a positive z, but I'm trying to figure out what value of z is that such that all the area in between the two is that it was 0.8064. Alright, so what we want to do here is we want to use the fact that we know that all of this area and all of this area, those two have to be the same, and also we know that the total area has to add up to be 1. Right? So if I want to know the area of these two pieces, I can say 1 minus 0.8064. Alright, so if I say 1 minus 0.8064, that's going to give me the area of the two regions. Alright, so let me do that in a calculator. 0.1936. Alright, I'm going to come back to my calculator in a second. So 0.1936. So that's for both of these. All right. So what would the area in one of those be? Well, if we know that they have to add up and they're symmetric, they're the same area here and here, then all we need to do is take that and divide it by 2, and that'll give me the area of each one. So divided by 2. All right, so 0.0968. So here's what I know without a shadow of a doubt. I know that that area is 0.0968, and I know that that area is 0.0968. So you say, well, how can I use that to help me find the z value? Remember, I told you it's going to be the same z here and here, it's just that one of them is going to be negative. So I'm looking for an area. If I can find an area in the table close to 0.0968, then that's going to be this negative z. All right, so 0.0968 is what I'm looking for in my table. Now let me show you. If you go to the same table that we've been going to, like if I go to that same table, this one, we start out at 0.5. That's the smallest area, so we can't use that table. All right, we need to go to the negative infinity to negative z table. That's because that's where all the negative z values are. So you see these areas in here are a lot smaller. So we need, what are we looking for? 0.0968. So I need to scroll down, 0.0985. Let's see, we're making it closer than that. Look at that, 0.0968. So this is going to be the negative z value. But remember, I told you they're the same number, it's just that one of them's negative and one of them's positive. So this is negative 1.30. So a z-score of negative 1.30, I would have an area of 0.0968 to the left. So what does that mean? That means that this right here, that's negative 1.30, and that means that would be positive 1.30. It asks for just the value of z, so it's not asking us to put in both of them. It just says find the value of z such that this area lies between the negative of that and that. So you put in just 1.3. All right, so now I'm going to show you how the area under the curve can be used for probability. All right, this problem says the diameters of ball bearings are normally distributed, or distributed normally. The mean diameter is 144 millimeters, and the variance is 36. That's important that it says variance. Find the probability that the diameter of a selected bearing is greater than, that's also important, greater than 147. Okay, so we got a lot of good information in this word problem that I'm going to write down first before I start actually doing math. Okay, so this is problem number 20. So a couple of things. We were told that the mean of a ball bearing is 144. We were also told that the variance, remember that's the standard deviation squared, was 36. Also, we were looking for the probability that the bearing, I'm going to call x, is greater than 147. All those are very important. Now we need to make a z-score out of that. My z-score formula is x minus mu over sigma. All right, so, or if that's for population, it gives you the same answer, or if you had z equals x minus x bar over s. Well, we don't have sigma, we have sigma squared. So to find sigma, we need to take the square root of both sides, right? So standard deviation is going to be equal to the square root of 36, or 6. So now let's plug those in my z-score formula. So my x is 147. So then minus my mean was 144, and my over the standard deviation was 6. So subtract there, you get 3 over 6. Remember, z-scores are always rounded to 2 places. So if I say 3 divided by 6, I get 0.5. To be more correct, 2 places would be 0.50. All right. And now, the other important part, the greater than. So what greater than means is that we want to figure out the area to the right of that z-score. Okay? So remember, right here in the middle we have a z equals 0. 0.5, that's to the right of the center. So I'm just going to guess. I'm going to say about right here. That's going to be where z equals 0.5. Now, since this was a greater than, the probability that a randomly selected ball bearing would be greater than 147, that means we want the area to the right. And remember, our tables do not give us the area to the right. The tables are going to give us the area to the left. So to find the area to the right, I'm going to say 1 minus whatever area I get for z equals 0.50. So I need to go to my table. So let's go to the table. All right, so z table, and I'm going to go to 0.50. So that's this value right here, 0.50. So I'm going to say, if I say 1 minus this, that will give me the area to the right. So 1 minus 0.6915. 0.6915. So if you use a calculator and you subtract that, you'll get 0.3085. So what that actually means is, for this particular company, there is a 30.85% chance that if I randomly select a ball bearing, that it'll have a diameter greater than 147 if it was millimeters or whatever it was. So that's what I want to put in, 0.3085. And I'll put in 2/8. Let me go back. Alright, this one is very similar. This one does give you standard deviation though. It doesn't give you the variance, so you're not going to have to find the variance. It says the standard deviation of this light bulb, 25 hours. The mean lifetime is 590 hours. Find the probability of a light bulb lasting more than 612 hours. Okay? No, that's not what it said. It said it's at most. Alright. Find the probability of a light bulb lasting at most 612 hours. So what does at most mean? Let's think about that. At most. So if you scored at most a 90 on a test, that means that you would have scored either a 90 or below, right? At most actually means less than or equal to. So we're trying to find the probability that that light bulb is going to last at most 612 hours. That's very important, because less than tells us to do something just a little different here. Okay, so let's write down what we have. We have that the standard deviation is 25. We were also given that the mean was 590 hours. And that value of x that we're going to look at, remember, was 612. So at most is what it said. At most, 612 would be less than or equal to. So what we want to do is convert that over to a z-score. So z equals x minus mu divided by sigma. So let's punch that in the calculator and round it to two places. So 612 minus 590 divided by 25. That's 0.88. So it was already rounded to two places. So 0.88. That's my z-score. So somewhere under this curve, you know, right here in the middle, remember z equals 0. Somewhere under this curve over here, I have a z equal to 0.88. Now the problem, the at most, remember, means less than or equal to. Less than means to the left of that. To the left. Well, luckily, that's the way that our tables are. Our tables give us the area to the left of the z-score. All right, so what we're going to do is we're going to go in and look at the table. And we're trying to find an area from a z-score. So we look at the z-score, 8.8. All right, so you can see that gives us an answer of 0.8106. So since we were looking for less than or equal to, 0.8106 is what we use. Okay. So use the value from the table if it's a less than or equal to on these. And I want to double check that I put in the right value. So 8.8106. Okay. 8106. Very easy just to type something in wrong like that. I should have just copied and pasted it. Alright, this problem is exactly the same. It tells us the mean income of firms in the industry for a year is $35 million with a standard deviation of $7 million. If incomes for the industry are distributed normally, what is the probability that a randomly selected firm will earn less than $39 million? So, of course, we need $35 million. That's going to be our mean. $7 million is our standard deviation. $39 million is going to be our x, and we're looking less than. I like less than problems because on those, I can just take the value from the table. Okay? So, let me write down everything that we're doing here. So remember, we had a mean of 35,000. So you can call it x bar or you can call it mu here. It really doesn't matter. It's our best estimate that we have. So 35, I may have said 1,000. 35 million was our mean. And then our standard deviation we're given. So for this problem, you could write sigma or you could write S. It's going to be the same thing. It's 7 million. And then our x value. So the thing that we're talking about being less than or greater than, that was 39 million. So to find this z-score, I'll say x minus mu over sigma. So that's 39 million minus 35 million divided by 7 million. All right. So it's going to be, let's see, it's going to be 4 million divided by 7 million. So 4 million divided by 7 million. All right, so this is my z-score. Remember, z-scores are rounded to 2 places always. So 0.57 is the z-score that I have to use. Now, since the problem said less than, that's the problems where I will take the area to the left. And remember, that's the way that our tables that we use are actually made. So somewhere there I'll have a z of 0.57. And in the tables, the areas are cumulative from left to right. Okay? So let's look up a z-score of 0.57, and we take the answer from the table. So I've got to go to the standard normal table, negative infinity to 0. Don't click 0 z or 0 to z. Click this one. And I use a z-score of 0.57. So this value right here. And again, I'm just going to copy and paste it so I don't forget it. There you go. That's the answer. Alright, select the normal probability plot which best indicates a normal distribution. So for a normal distribution, the plot is going to be around the line that's given. It's going to be the one that's the closest around the line. You can see this has some stuff down here, and this has some stuff down here. That has some stuff above. It's okay to be above and below, but it really, you want it to be along the line. So that one's a little closer along the line than the previous one, but let's keep looking. Oh man, these are like right on the line. So this is the best one right here. This is my top choice so far. Oh yeah, this one still has stuff below here and here, so no, it's got to be this one, the one that's closest along that line there. It's got to be the answer. All right, select the histogram that best represents a normal distribution. So the histogram you want, you see all these histograms? You want the one that kind of goes up, then gets to a high point, and then goes back down. So it's got to be this first one here. You see how it goes up, and then goes back down. It kind of looks like, if I was to connect the points here, it would look like a bell-shaped curve, right? The curves that I've been drawing, the bell-shaped curves, so that's normal distribution. So this is this first one right here. If you look at all of them again, you see it needs to go up and then back down. And this one kind of does, but it starts up and it goes down, and it goes up and it goes down. So it's not that one. This one kind of looks right too, but you can see it's this one is skewed to the right because we have lots of little values over here on the right. So that's got to be the one right there. Alright, consider the probability that no less than 82 out of 291 flights will be delayed. Choose the best description of the area under the normal curve that will be used to approximate the binomial probability. So normal distribution can be used to approximate binomial probability distributions. And so what does no less than 82 mean? No less than. So like 82 would be the biggest number, right? Or no, it would be the smallest number, right? If it's no less than 82 out of 291. Well, what we have to do whenever we are using this as an approximation is you have to subtract 0.5 from the smallest number that you're going to use. No less than 82, we'd have to subtract 0.5 from that. So what do you get when you subtract 0.5 from 82? You say 82 minus 0.5, you get 81.5. Okay? 81.5. So we would want to use 81.5 or bigger if it's no less than 82. So it will be the area to the right of 81.5. Okay? Hopefully this helps you. If you have any question about any of these problems that I've worked out, I know I've kind of went slow But if you have any questions, feel free to email me, and I will try to get back with you as soon as possible. Make sure you take your test. Best of luck. Have a great day, and I look forward to hearing from some of you soon. And this is what I hope everybody makes right here. 100%. Have a good one.